Welcome to the Yetimkhana and Madrasas Anjuman Khairul Islam's Pune College of Arts, Science and Commerce, Camp Pune 1. Myself, Dr. Arif Tamboli, working as Associate Professor in the Department of Electronic Science. So let us proceed for the second lecture of IC 555 as a stable multivibrator. In last lecture, we have studied four different blocks of IC 555 as a stable multivibrator. Now in this lecture, let us join all four different blocks of IC 555 and proceed for a block diagram of IC 555. So you can see here a title over block diagram of IC 555. So as I told in the previous lecture, there are four blocks. Number one, potential divider circuit designed by three resistors each of 5 kilo ohm. Number two, two comparators. So here you can see 5 kilo ohm, 5 kilo ohm, 5 kilo ohm, three resistors forming potential divider circuit. One is the 5 kilo ohm, second is 5 kilo ohm, third is 5 kilo ohm. Two comparators, upper comparator and lower comparator. Then flip-flop, RS flip-flop and then transistor or like this. So here it is very simple to understand what are the four blocks which we have already studied. Now let us interconnect the four blocks. So how we are going to interconnect? So the interconnection between the block is also very simple, and we have to take a little bit care while interconnecting the block to each other. And the care is like that: draw three resistors such that they will have a little bit separation or the gap between them. So here you can see very easily, this is 5 kilo ohm resistor, this is 5 kilo ohm resistor. You have to draw a resistor such that this is the R1, this is R2, this is R3. There will be gap between this, because in between this gap we have to draw a comparator. Similarly, between R2 and R3, again put a little bit gap, because in this gap or in front of this gap we have to draw a comparator like this. So you know that three resistors forming potential divider circuit. Upper terminal of first resistor R1 is declared as a power supply of the IC 555 and it is pin number 8, where we are applying 15 volt as on today's example. Last resistor R3, last terminal is declared as a pin number 1 of the IC 555, that is ground. So when you apply 15 volt over here, these three resistors simply will work as potential divider, and at this point 10 volt will come, because 2/3 voltage at this point comes here, and that 2/3 is the of 15 volt is nothing but 10 volt. 5 volt will come over here, because 1/3 of 15 volt is a 5 volt, so 5 volt will come here. Now as I told you in the previous lecture, upper comparator is drawn such that minus sign is upper side, plus sign is lower side. So when you draw this comparator in front of the gap between R1 and R2, straightway connect the junction of R1 and R2 to the minus terminal. And this junction is also taken out and called as a pin number 5, which is called control voltage, which we have discussed earlier. Now let us come to the lower comparator. As we have drawn the lower comparator in front of the gap between R2 and R3, the junction of lower comparator is connected straightway to the upper terminal of this comparator, and we know that the lower comparator is drawn such that upper terminal is positive sign, that is non-inverting. Let us take the output of lower comparator, that is pin number inverting pin of lower comparator, that is pin number 2, because this is second comparator, and second comparator's second pin, this is called pin number 2. This is a control voltage which is called pin number 5 CV, control voltage. Below the pin number 5, write pin number 6, advancement. which is lower terminal of upper comparator. So like that, these two blocks are interconnected. That is the block of potential divider circuit and block of comparator. So this is well interconnected and pins are taken out. So by this time we have completed overall 5 pins. Pin number 8 has a power supply, pin number 1 as a ground, pin number 5 as a control voltage pin number 6 which is lower terminal of upper comparator, and pin number 2 lower terminal of lower comparator. Now let us go to the next step. The output of comparator, which will remain either in logic low voltage level or zero voltage level. So here I have written LV. Let us see how does it comes LV. Here I have written HV. That also we are going to study how does it comes to HV. So output of these two comparator will be given to RS flip-flop. So very simple. Straightway RS flip-flop is connected in front of two comparators, and this is RS flip-flop. We know that RS flip-flop used in IC555 is having active low reset pin. So this active low reset pin we have connected to the power supply to avoid the resetting. Q is here, Q bar is here. Now Q is directly taken to the output of IC555, and this is called pin number 3, and that is the output pin of IC555. Q bar. Q bar is a complement of Q which is taken out and used to drive the transistor either as an open switch or as a closed switch. So whenever Q bar is in logic 0, it will behave as an open switch. And whenever Q bar is in logic 1, transistor will behave as a closed switch. We'll see that. Now, collector of transistor is taken out and it is declared as a pin number 7, which is called discharge pin. And in this way, I hope we have succeeded in interconnecting all 4 different blocks which we have studied: potential divider circuit, comparator, flip-flop, and transistor as a switch. Now let us understand how does these 4 blocks works, and they generate the square wave at the output. Square wave is nothing but logic 1, that is a high voltage level for some time. Thereafter it is coming down, that's why downgoing arrow. Then it remains in logic 0. Then after some time again it goes up and then again remains in logic 1. So in this way neither logic 1 is present nor logic 0, and that's called square wave, and it is output of a stable multivibrator. Now this is internal block diagram of IC555, which is used to generate the square wave at the output by connecting externally connected capacitor C along with RA and RB in the circuit diagram. So after this we are going to observe the circuit diagram, and then we are going to study how does all these 4 block works. Now let me tell you one thing here, why I have written here LV is equal to 0. Because the moment as soon as I apply the plus 15 volt, 10 volt comes here. This terminal is open terminal, so I have considered open terminal voltage as a 0 volt. So when this is 10 volt and this is 0 volt, voltage at negative terminal is greater, therefore it is LV. When you apply 15 volt, 5 volt come here because 1/3 of Vcc. So 5 volt is there at positive terminal, and negative terminal, which is pin number 2, is open, means I have considered this as a 0 volt. So when I consider this 0 volt, this is 5 volt, so voltage at positive terminal is greater, that's why it is HV, means high voltage. And in this way you will understand that in the beginning set is 1, therefore Q is 1, and when Q is 1, the output is HVL. So in the beginning always remember output of IC555, when it is used as a stable multivibrator, Q is going to remain in high voltage level and Q bar is in low voltage level. Therefore in the beginning transistor behaves as open switch. So this is the basic understanding. Now let us proceed for the circuit diagram. of IC555 as a stable multivibrator. Along with this block, three components are added in case of a stable multivibrator circuit diagram, and that three components are nothing but externally connected RA, RB and C. They will come over here in this region. These are internal diagram, means internal blocks. So let us proceed for the circuit diagram of IC555. So this is circuit diagram of IC555 as a stable multivibrator. So look into circuit diagram. In circuit diagram, what we have done, that we have simply drawn a square block of IC555. Simple square block, this. And inside this square block, what is there, that already we have studied. So inside this square block, there are three resistors, each of 5 kilo ohm. There are two comparators. There is RS flip-flop. There is transistor as a switch. So like this internal block diagram which we have already studied. Now circuit diagram, when we draw, we will simply draw a square box indicating the pins. Look at pin number 8 and pin number 1. They are just at the top end and at the bottom end, because in between pin number 8 and 1, three resistors each of 5 kilo ohm comes into picture. Here, after comparator there is a flip-flop, and this is the pin number 4 of the flip-flop, which is reset pin. So we connected it to plus Vcc. Pin number 3 is the output of flip-flop Q, so it is over here. Now Q bar is Q bar is going to the base of transistor, and pin number 7 is the collector of transistor, which is the discharge pin. Pin number 7 is the collector of transistor, which is a discharge pin, which we already studied in the previous block diagram. What is pin number 6 and pin number 2? Pin number 6 is upper comparator's lower terminal, that is positive terminal of upper comparator. And what is pin number 2? Pin number 2 is a lower comparator, means second comparator's lower terminal. And second comparator's lower terminal is nothing but negative terminal. So this pin number 6 and 2 are short circuited to each other. Now pin number 5, that is a control voltage pin, which we don't want to connect anywhere. So instead of leaving it open, we connected it through a capacitor to the ground. So the reason behind this, to connect this through a capacitor to the ground, is, I will go again in the previous diagram and then I will explain you here. So here you can check now that our this one, pin number 5 is this. So this pin number 5, if I connect to the capacitor and another terminal of capacitor to the ground, then that capacitor will get charged to 10 volt, and this capacitor we are connecting very small, therefore within a fraction of second that will get charged to 10 volt, and it will not affect the 10 volt, it will hold the 10 volt. So always the control voltage pin, when it is not used, instead of leaving it open, it is connected through capacitor to the ground. And as I told you that pin number 6 is the lower pin or lower terminal of upper comparator. Pin number 2 is also lower terminal of lower comparator. And pin number 7 is the discharge, that is collector of transistor. Now let us proceed further. So here, if you understand this circuit diagram, then in this circuit diagram, you will come to know that RA and RB and C are again in series, but all these three components are externally connected. And here, very important thing you note down, that IC555 simply changes the output Q of flip-flop from logic 1 to logic 0 and generates square wave. But to change the output of the flip-flop Q from logic 1 to 0 and 0 to 1, we must change the inputs of the flip-flop. And the inputs of the flip-flop are driven by the output of comparator. Therefore, to change the output of flip-flop, we must change the input of the flip-flop R and S, and to change the input of the flip-flop R and S, we must change the output of comparator in the form of high voltage or in the form of low voltage. Therefore, in this circuit diagram, externally connected capacitor C is charged through RA and RB when power supply is connected. Externally connected capacitor C charges through RA and RB when power supply is connected. But when this charging of the capacitor takes place, the voltage across capacitor goes on increasing. Means voltage at the pin number 6 and 2 goes on increasing, which we are going to study in the next diagram. So this increase in the voltage at the pin number 6 and 2 is exponential in nature. Okay, and that exponential increase in the nature due to not charging of the capacitor with the help of constant current source. So in this diagram, the current is not a constant with which the capacitor is charged. So we'll study the next thing here. But remember, the voltage across capacitor when we turn on the power supply goes on increasing exponentially, and it will charge till 2/3 of Vcc, and again it will discharge till 1/3 of Vcc. That just you remember now. In the next diagram you are going to understand in detail. So in this diagram it is very simple. Total time t is this, where there is a logic 1 and logic 0. So logic 1 time is called t on, logic 0 time is called t off. So f is equal to 1 by t. Now let us concentrate on this part of the circuit which is externally connected, and what happens when we turn on the power supply with this external part. So as you know that pin number 7 is a discharge pin. So let us proceed for the next diagram. So look at this here. When I said externally connected resistor RA, RB and C are in series and connected to the power supply, but now I have introduced here a switch S. Now this switch S is open, therefore this power supply plus Vcc of 15 volt is not applied to RA, RB and C. Therefore initially the capacitor is a discharge, that is Vc is equal to 0 volt. So in this way this initial capacitor is a discharge because power supply is not connected. But when the power supply is connected through the switch S, by closing the switch S, no doubt the current I will start flowing through RA, through RB and capacitor C will start charging. And therefore here in the diagram number 1 below I have shown the voltage across capacitor Vc is 0 volt. Okay. Here in this diagram what we have shown, the capacitor starts charging, therefore voltage across capacitors will go on increasing. So here the voltage across capacitor goes on increasing. So it will charge to 2/3 of Vcc, that we'll see later. Now intentionally I have shown here one more path, that is called your discharge path of the capacitor. So here this is a transistor as an open switch. So you might have been understood in the beginning Q is 0 and Q bar is, sorry, Q is 1 and Q bar is 0. So in the beginning when Q is 1 and Q bar is 0, transistor is an open switch. So pin number 7 is not connected to the ground. Therefore the total current after closing the mains power supply switch, the total current goes through RA, RB and charges the capacitor. The current will not go to this path because transistor is open switch. Now when capacitor gets charged just above 2/3 Vcc, just about 2/3 Vcc means 2/3 Vcc is our 10 volt. When it is going just about 2/3 Vcc, output of comparator changes and output of flip-flop also changes. So flip-flop output Q becomes 0 and Q bar becomes 1. So when Q bar becomes 1, the transistor behaves as a closed switch. So what happens here? When transistor is a closed switch, the already charged capacitor to the value of 2/3 voltage will start discharging now through RB only, because this point is connected to the ground, short circuited. So capacitor discharges through RB. This is one action happens. I have shown with the help of red pen. Another action, as switch S power supply is continuously applied, the current flowing from power supply goes through RA and current observes a short circuit path, least resistance path. Therefore, current goes through short circuit path. And capacitor C, which was already charged to 2/3 Vcc, will discharge through RB and discharging will start like this. So this discharging of capacitor will take place only up to 1/3 of Vcc, means 5 volt, and not below that or just below the 1/3 of the Vcc by few millivolt. So it is just said that it is up to 1/3. So in this way here, capacitor gets discharged to 1/3 Vcc. Capacitor will get charged to 2/3 Vcc. But remember, charging takes place through RA and RB, and discharging takes place only through RB. So now let us proceed to the internal block diagram along with this externally connected capacitor. But in the beginning, we'll consider that capacitor voltage is 0 volt. So now let us see here. So here now you will understand that this diagram here, we have connected plus 15 volt. When we connect the plus 15 volt to the IC at a pin number 8 over here, that 15 volt is simultaneously applied to the RA, RB and C. In the beginning, I have considered this capacitor is initially discharged. Vc is equal to 0 volt at a time t is equal to 0 as soon as I turn on the power supply. The moment as soon as I turn on the power supply, the voltage across capacitor C, that is Vc, is equal to 0. So this 0 volt we have applied at pin number 2 and pin number 6, because pin number 6 and 2 are short circuited. So this pin number 6 is at 0 volt, so we have written here 0 volt. Pin number 2 is also at 0 volt, so here we have written 0 volt. When you apply 15 volt to the IC, the potential divider circuit will connect this terminal to 10 volt, that is 2/3 Vcc, this terminal to the 5 volt, that is 1/3 of Vcc. So in the beginning, let us see the inputs of the comparator. This is going to remain 10 volt, total of Vcc. This is going to remain 5 volt, 1/3 of Vcc. Here 0 volt because capacitor is initially discharged. And this pin number 6 voltage, whatever it is there, same voltage will be pin number 2 because both are short circuited pin and connected to capacitor. So this voltage is again 0 volt. So if you look at the upper comparator, this terminal minus terminal is at 10 volt and this is 0 volt, so output is low voltage. If you look at the lower comparator, positive terminal is 5 volt, negative terminal 0 volt, the output is high voltage because this voltage is greater. Therefore, in the beginning, as soon as you turn on the power supply, it is said that the Q is in logic 1, so output is HPL. Q bar is in logic 0, so this 0 will come over here. Transistor will not conduct because base voltage 0 volt, so emitter to base junction is not forward bias and transistor will behave as open switch here. Therefore, collector of transistor, which we have taken with the help of a red pen, you follow this, you follow this, you follow this, like this, and it will come to the junction of RA and RB, that is discharge pin. That is discharge pin. That's why in the previous slide I have shown you this as a discharge path. Capacitor discharges through RB. But now, as a transistor is open, when we turn on the power supply, in the beginning Q is 1, Q bar is 0, transistor is open, therefore entire current goes through RA, then goes through RB, and then goes to capacitor C and charging action capacitor starts. Now when the capacitor starts charging, definitely this voltage will go on increasing from 0 volt to 1 volt, then 2 volt, then 2 volt, 3 volt, then 4 volt and then 5 volt. Like that, first of all, this voltage across capacitor Vc will cross the level of 5 volt. That is 1/3 voltage. Will cross the level of 5 volt, that is 1/3 voltage. And thereafter it will cross 6 volt, it will cross 7 volt and it will cross 10 volt. But now we'll see that when the capacitor crosses the level of 5 volt, one third of Vcc, the voltage written over here will not be 0 volt. The voltage written over here will also not be 0 volt. So in the next block diagram, we will see that this will be remaining 10 volt, will not draw these three resistors. This will remain 5 volt, and this voltage will consider that capacitor is just cross the one third of Vcc, and then what action happens that we'll see. So let us come here. Yes, now look at this. We have shown here 10 volt because it is a fixed two third. We have shown here 5 volt because it is fixed one third. Now, as our capacitor starts charging through RA through RB and current goes to capacitor, and capacitor voltage goes on increasing, and therefore this is plus and this is minus, and this voltage definitely cross 5 volt. So I have written here 5.1 volt instead of 0. So when I written here 5.1 volt, these two terminals are short circuited. So here also will be 5.1 volt. Now when these voltages are just above one third Vcc, see output, lower terminal will go into the logic 0 now. Earlier lower terminal was in logic 1 because this was less than 5 volt. Now as soon as this voltage crosses the 5 volt, voltage at negative terminal becomes greater than voltage at positive terminal. Therefore this will cross the logic, this will change to the logic 0, and now the both inputs of the flip-flop remains into the logic 0. Therefore, as I told you in previous lecture, as long as both inputs are having in logic 0 0, the output will continue to remain in logic 1. The output will not change. So in this way, our capacitor started charging from 0 volt to 1 volt, 2 volt, 3 volt, 4 volt, 5 volt or 5.1 volt, that is cross the one third voltage, but output logic 1 will continue to remain there. Now we want to see that how long time HVL remains there. So capacitor will go on further charging from 5.1 volt to 6.1 volt, 7.1 volt, 8.1 volt. Like that, capacitor will just cross the two-third of Vcc 10 volt. So in this way, the moment as soon as the capacitor just reaches to two-third of Vcc, entire situation further changes, and that we are going to see. So remember, HVL is continued from 0 volt even though the capacitor is crossing one third Vcc and it is charging towards the two third of Vcc. Now let us proceed to the next block, and that block is nothing but this one here. So now I have written here capacitor is charging above 5.1 volt, so it's 7.1, 8.1, 9.1, and this positive of the capacitor is at 10.1. So when I wrote here 10.1, here again it is a 10.1. Now you understood that the just above two-third Vcc capacitor charged, and when this voltage is just crossing two-third Vcc, upper comparators lower terminal becomes greater voltage than inverting input. Therefore, upper comparator's output, which was earlier 0, now it will become 1. And as soon as this output becomes 1, now the inputs of the flip-flop are not 0 0. Therefore, R is 1, S is 0. Therefore, flip-flop output will not remain in 1, it will go to 0. Flip-flop is reset. In this way, output HVL, which was there till the capacitor charges to two-third Vcc, but the moment as soon as capacitor just crosses two-third Vcc, output HVL will go to the logic LVL. And as soon as the output HVL goes to the logic LVL, because Q is 0, Q bar becomes 1. As soon as Q bar becomes 1, look at the Q bar, it is going to the base of transistor. 1 means high voltage. So emitter to base junction of transistor gets forward biased, and in this way transistor behaves as a closed switch. Collector of a transistor, which is pin number 7, so it is connected to the junction of Ra and Rb, and this junction of Ra and Rb, look at this junction, this is a jumper, then this is there, and then this is pin number 7 and then ground. So as soon as Q bar becomes 1, transistor behaves closed switch, and what happens here? The entire total current I, which was going to charge the capacitor, now that current will go through Ra, and then the current will get a least resistant path, that is short circuit path. So that power supplies current will go through Ra, and it will go through the short circuit path of the closed switch like this. This is number one. Number two, the capacitor which was already charged to the two-third of Vcc, that is just about 10 volt. So that capacitor gets discharged. So see this arrow, that capacitor gets discharged through Rb. Why? Because this terminal is connected to the ground. Therefore, this is a discharge path of capacitor. Whenever we short circuit the capacitor directly or through a resistor Rb, capacitor gets discharged. And in this way here, when transistor is forced into closed switch, the discharging action of the capacitor starts. Now you can easily understand, when discharging of capacitor starts, immediately this voltage which was about 10 volt, just about 10 volt, will come below 10 volt. Yes, but even though it comes below 10 volt, LVL will continue to remain there unless and until the capacitor gets discharged to the level of one-third Vcc. So now see here, let us consider this is less than 10.1 volt, 9 volt. So when this is 9 volt, this is also 9 volt. So when this is 9 volt, look at this. So this will become, this is 9 volt and this is 10 volt. So this will become low. This will become low because when it is a 9 volt and it is 10 volt, one two-third of Vcc is 10 volt. So this will become low. Now this is remaining low and this is also low because even though it is a 9 volt, the voltage at negative terminal is greater than 5 volt. So when both are low, as I told you earlier, the output of the flip-flop will continue to the previous state, that is logic 0. Now how long time it will continue to the logic 0? Let us come here. 9 volt, then 8 volt, then 7 volt, then 6 volt, then 5 volt, and just below 5 volt, means 4.99 volt suppose. When this voltage across capacitor, which is discharging now, goes below one-third Vcc, 4.99 volt, what happens here? This is already in the logic 0 because of here this voltage is less than 10 volt. And then when it is going 4.99 volt, 5 volt becomes greater than the 4.99 volt, and output of this will force to the logic 1, and this is already logic to the 0. Therefore flip-flop yes input will become 1, R will become 0, and Q will become 1. So LVL will go to HVL, and in this way, how long time LVL remains? Till the capacitor does not get discharged from two-third Vcc to one-third Vcc, LVL will continue. How long time HVL remains? Till the capacitor does not get charged from 0 volt to two-third of Vcc. Therefore here, if you look into this diagram, I have shown you the detail. So look at this. This is the voltage, this is the time. On x-axis there is a time. Now HVL is a logic 1 and HVL is always equal to plus Vcc of the IC. LVL is equal to logic 0. Now how long time HVL was there? HVL was there till the capacitor charges from 0 volt to two-third of Vcc. So here, so this is the time duration of HVL. Now this time duration is decided by you people because how long time the capacitor will take to go to two-third Vcc depends on three factors. Factor number 1 value of Ra, factor number 2 value of Rb, and factor number 3 value of capacitor C itself. because if the capacitor is very big and RA, RB are very small, then the charging will take place fast, but big capacitor it will take large time. Or if the capacitor is big and RA/RB in mega ohm, very less current will flow, very long time will require to charge the capacitor. So this charging time is decided by you from the value of RA, RB and C. Similarly, when capacitor charges just above two-thirds of the Vcc, that is just above 10 volt, the output of comparator changes and output of flip-flop also changes. So upper terminal of the flip-flop means Q will become logic 0 and Q bar will become logic 1 and transistor will go into closed switch. Therefore, discharging of capacitor takes place, but discharging of capacitor takes place from two-thirds of Vcc to one-third of Vcc. So this is there. Capacitor will never get discharged to 0 volt because as soon as the voltage across the capacitor goes below one-third Vcc, again the logic level 1 will appear. So like that here, how long time the logic level 0 will remain? Till the capacitor discharges from two-third Vcc to one-third Vcc. Remember, this is also decided by you because if the capacitor is big and if the RB, because capacitor discharges only through RB, low resistor, and if the RB is very less in ohm, the discharging takes place very fast, or this time can be very large if you select the value of RB in mega ohm. So discharging current will be very less. So this time can be large. So in this way, T charge is also decided by you. T discharge is also decided by you. Capacitor charges till two-thirds of Vcc. Capacitor discharges till one-third of Vcc. And in this way, HVL is logic 1 means plus Vcc. LVL is logic 0 means 0 volt. And you will get the generation of square wave at the output of IC 555, and this square wave is called a stable multivibrator. Here, whenever voltage level changes from high to low, it is marked by the downgoing arrow, that is also called as negative edge. Whenever voltage changes from low to high, it is marked by the positive upgoing arrow. So this is called positive edge. So upgoing arrow, positive edge. And total time T is the time between two adjacent positive edges or two adjacent negative edges. Adjacent. So like that here, this is the total time T. Now you can understand very easily that total time T is T charge plus T discharge. Time required to charge the capacitor and time required to discharge the capacitor. This is the one cycle. Positive edge, negative edge, and then positive edge. So here there is one cycle gets completed from this point to this point. And this total time T is T charge plus T discharge. And this if you calculate with the help of CRO, you can calculate the frequency by using formula F is equal to 1 by T. But remember, you can also get the frequency at the output, or you can also calculate the frequency at the output of IC 555 with the help of a formula F is equal to 1.44 divided by RA plus 2 times of RB bracket close into C. This is the capacitor. And if you take the value of RA in ohm, RB in ohm, and capacitor C in farad, convert all that value. If they are in kilo ohm, convert into ohm. If they are in mega ohm, convert into ohm. Capacitor C should be in farad. If it is in microfarad, convert it into farad. If it is in nanofarad, convert it into farad. So when you take all values in its basic unit, means resistor in ohm, capacitor in farad, then whatever calculation is then there, that is in hertz. And this is the formula. Again, look at this formula. In this formula, RA is there and 2 times of RB. Why there is a 2 times RB? The RB is a 2 times because while charging, RB takes place role, as well as while discharging, RB takes place role. RA is only one time because because see here, while when you consider this RA and RB, when power supply is on, RA and RB both are responsible for charging. RA and RB both are responsible for charging because current flows through RA as well as through RB and goes to C. But when the discharging takes place, when this switch is closed, only RB is responsible. So during discharging process of capacitor C, RB takes part, RA does not take the part. That's why in the formula, you'll observe that F is equal to 1.44 RA plus 2 times of RB into C. Now very simple after understanding all these things. If we simple ask a question to the student, if RA is equal to RB, then what will be the shape of square wave? So when RA is equal to RB, say RA also 1 kilo ohm and RB also 1 kilo ohm. So what is the total resistance which is taking part for charging capacitor? Because for charging RA and RB both taking part, therefore total resistance taking part for charging capacitor is RA plus RB. Therefore time required to charge the capacitor is double. See here, this time required to charge the capacitor is double than the time required to discharge. So here we have intentionally drawn this as a half of this. So if RA equal to RB, the charging time is double and discharging time is half of that. Why? Because during discharge only RB takes part. Therefore only 1 kilo ohm more resistance will come into picture during discharge because we have considered RA 1 kilo ohm and RB 1 kilo ohm. So total resistance for charging will be 2 kilo ohm. So charging time is double and discharging time is half. Therefore when RA is equal to RB, this type of waveform will come. And if you want to generate a perfect square wave of symmetric nature, means HVL equal to LVL. Remember, RB should be very, very large and RA should be very, very small. Why? Because if RA is small, let us go to that diagram again. If RA is small, say 1 kilo ohm, and RB is very large, say 100 kilo ohm, so total resistance taking part in charging is RA 1 kilo ohm plus RB 100 kilo ohm. So total is 101 kilo ohm. But during discharge, only RB taking part, but RB is 100 kilo ohm. Therefore, discharging is 100 kilo ohm. Charging is 101 kilo ohm. Now, if you compare 100 kilo ohm, 101 kilo ohm, sorry, 100 kilo ohm is the lower resistor and 101 kilo ohm is the total combination. So like that, charging time and discharging time will be very close to each other. And in this way, to have a symmetric square wave, it is better to proceed for having a RB as possible as large and RA as possible as small. So in this way, I will conclude that the lecture for IC 555 as a stable multivibrator generation of square wave at the output is over, and thank you for watching this video. If you have not understood any concept, watch it again and again, and I hope you will understand. I have explained each and every block in detail. Thank you very much.